friends. I am handling today properties of fluids, the fundamental of fluid mechanics at first, and I have to know about the properties of fluids such as density, specific weight, specific gravity, compressibility, surface tension, capillarity, etc. So first let's see what density is. Density is defined as the ratio of mass of a fluid to its volume, and its unit is kg per meter cube. The value of density of water is 1000 kg per meter cube. Then specific weight or weight density. Specific weight or weight density of a fluid is the ratio of the weight of the fluid to its volume. Therefore, its unit is Newton per meter cube. Also, specific weight is equal to rho into G. Then specific volume. Specific volume of a fluid is defined as the volume of a fluid occupied by unit mass or volume per unit mass of a fluid. And its unit is obviously meter cube per kg. Specific gravity. Specific gravity is a dimensionless number for any fluid, and it is defined as the ratio of the weight density of a fluid to the weight density of a standard fluid. The standard fluid is usually taken as water. Therefore, density of a liquid is equal to specific gravity into density of water. For example, the specific gravity of mercury is 13.6 and the density of mercury is 13.6 into 1000, 13,600 kg per meter cube. So now we'll see some of the problems related to these properties. Calculate the specific weight, density and specific gravity of 1 liter of liquid which weighs 7 Newton. Volume 1 liter is 10 power minus 3 meter cube. Weight is 7 Newton. Specific weight is therefore weight by volume 7000 Newton per meter cube. Density rho is equal to W by G. So it is 7000 divided by 9.81, 713.5 kg per meter cube. Whereas we have specific weight is weight by volume 7000 Newton per meter cube. Specific gravity is density of the liquid 713.5 divided by density of water 1000, 0.7135. We'll move to the next simple problem. Calculate the density, specific weight and weight of 1 liter of petrol of specific gravity 0.7. Volume is 10 power 3 meter cube. Density is specific gravity into 1000, 0.7 into 1000, 700 kg per meter cube. Then specific weight is rho into G, 700 into 9.81, 6867 Newton per meter cube. And we know specific weight is equal to weight by volume, and it is W divided by 0.001, and W is equal to 6.867 Newton. Next property is viscosity. Viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. When two layers of a fluid distance dy apart move one over the other at different velocities, u and u plus du as shown in figure, the viscosity together with the relative velocity causes a shear stress acting between the fluid layers. And this shear stress is proportional to the velocity gradient, and shear stress is equal to mu into du by dy, where mu is called coefficient of dynamic viscosity. and du by dy may be taken as the rate of shear strain, and unit of viscosity you have to see that mk is a system of unit is kgf second per meter square. cgs unit of viscosity dyne second per centimeter square. SI unit of viscosity Newton second per meter square Pascal second, and 1/10 of Newton second per meter square is also used as the standard unit of viscosity, which is 1 pies. Okay, 1 pies is equal to 1 divided by 10 Newton second per meter square, and centipies is 1/100th of pies, and viscosity of water at 20 degrees Celsius is 1 centipies. Kinematic viscosity is defined as the ratio between the dynamic viscosity and density of the fluid. It is denoted by mu by rho, and its unit is centimeter square per second, 10 power minus 4 meter square per second. 10 power minus 4 meter square per second, that is 1 stoke, and 1 centistroke is equal to 1/100th of stoke. Newton's law of viscosity states that shear stress of fluid element layer is directly proportional to the rate of shear strain. The constant of proportionality is called the coefficient of viscosity, mu. Okay. Fluids which obey this relation are known as Newtonian fluids, and which do not obey these are called as non-Newtonian fluids. Then you have to see about the variation of viscosity with temperature. Temperature affects the viscosity. The viscosity of liquids decreases with increase of temperature, while the viscosity of gases increases with increase in temperature. The expression for variation is given for liquids and for gases also. Then we'll see the types of fluids. The fluids may be classified as ideal fluid, which has no viscosity, okay, and real fluids which possesses viscosity, Newtonian fluids which obey the Newton's law of viscosity, non-Newtonian fluid, and ideal plastic fluid. In ideal plastic fluid, shear stress is more than the yield stress, and shear stress is proportional to the rate of shear strain. And in velocity gradient, we'll see some of the problems. If the velocity distribution over a plate is given by u is equal to 2/3 of y minus y square, in which u is the velocity in meter per second at distance y meter above the plate, determine the shear stress at y is equal to 0 and y is equal to 0.15 meter. Assume dynamic viscosity of fluid as 8.63 pies. So expression u is given. Determine du by dy. It is 2 by 3 minus 2 by y. Then find out this velocity gradient values at 0 meter, 0.15 meter. Now we can find out the shear stress at these points using the velocity gradient. Tau naught is equal to 0.5756 Newton per meter square, and at 0.15 meter it is 0.3167 Newton per meter square. We'll move to the next problem. A plate 0.025 millimeter distance from a fixed plate moves at 60 cm per second and requires a force of 2 Newton per unit area, 2 Newton per meter square to maintain this speed. Determine the viscosity between the plates. Distance between the plates 0.025 meter. Velocity of upper plate U is zero point 0.6 meter per second. Force on upper plate 20 Newton per meter square. And this is the, 2 Newton per meter square, and this is the value of tau. Let the viscosity be mu. Tau is equal to mu into du by dy. Change in velocity is 0.6 meter per second. Change of distance 0.025 into point into 10 power minus 3 meter. Therefore, tau is equal to 2 Newton per meter square. So from this expression, substitution, upon substitution, mu is equal to 8.33 into 10 power minus 4 pies. Let's see the next problem. A flat plate of area 1.5 into 10 power 6 millimeter square is pulled with a speed of 0.4 meter per second relative to another plate located at a distance of 0.15 mm from it. Determine the force and power required to maintain this speed if the fluid separating them is having viscosity of 1 pies. Area of the plate 1.5 meter square. Speed du 0.4 meter per second. Distance between the plates dy 0.15 into 10 power minus 3 meter. Mu is 1 pies 1 by 10th Newton second per meter square. Using the equation tau is equal to mu du by dy, you get shear stresses 266.66 Newton per meter square. And force is shear stress into area 400 Newton. Power required is force into velocity F into U 400 into 0.4 160 watts. Another simple problem. Determine the intensity of shear of oil having viscosity 1 pies. The oil is used for lubricating the clearance between a shaft of diameter 10 cm and its journal bearing. The clearance is 1.5 mm and the shaft rotates at 150 rpm. Solution, we'll see the solution here. Mu is 1 pies, diameter 0.1 meter, distance between the shaft and bearing 1.5 into 10 power minus 3 meter. Speed of the shaft 150 rpm. Therefore, tangential speed is pi dn by 60 0.785 meter per second. Using the equation tau is equal to mu into du by dy, you get the value of shear stresses 52.33 Newton per meter square. Another simple problem on inclined plane. Calculate the dynamic viscosity of an oil which is used for lubrication between a square plate of size 0.8 meter by 0.8 meter and an inclined plane with an angle of inclination 30 degrees as shown in figure. The weight of the square plate is 300 Newton and it slides down the inclined plane with a uniform velocity of 0.3 meter per second. The thickness of oil film is 1.5 mm. So area is 0.64 meter square. Thickness of oil film 1.5 into 10 power minus 3 meter. Viscosity, take it as mu. Component of weight acting on the plane is W cos 60, 300 cos 60, 150 Newton. Therefore, shear force on both bottom surface of the plate is 150 Newton. Shear stress is force by area 150 divided by 0.64. And from the expression tau is equal to mu into du by dy, you get mu as 1.17 Newton second per meter square, that is equal to 11.7 pies. Another simple problem. Two horizontal plates are placed 1.25 centimeter apart. The space between them being filled with oil of viscosity 14 pies. Determine the shear stress in oil if upper plate is moved with a velocity of 2.5 meter per second. Distance between the plates 0.0125 meter. Viscosity mu 14 pies, 14 by 10 Newton second per meter square. Velocity of upper plate 2.5 meter per second. Shear stress is given by the expression tau is equal to mu du by dy. du is 2.5 meter per second, dy 0.125 meter. Therefore, shear stress is 280 Newton per meter square. Then another simple problem. Another simple problem will see the space between two square flat parallel plates is filled with oil. Each side of the plate is 60 centimeter. Thickness of oil film is 12.5 mm. The upper plate which moves at 2.5 meter per second, requires a force of 98.1 Newton to maintain the speed. Determine dynamic viscosity of oil in poise and kinematic viscosity. Area is 0.36 meter square. Thickness 12.5 into 10 power minus 3 meter. U is 2.5 meter per second. Change in velocity is 2.5 meter per second. Force required 98.1 Newton. Shear stress is force by area 98.1 divided by 0.36 meter square. Mu is dynamic viscosity. So from the expression tau is equal to mu into du by dy, you get mu is equal to 13.635 pies. Okay. And the mass density of oil is, specific gravity being 0.95, it is 950 kg per meter cube. Now using the relationship for kinematic viscosity is mu by rho, you get the viscosity as 0.001435 into 10 power 4 centimeter square per second. So it is 14.35 Stokes. Another simple problem here. Determine the kinematic viscosity of an oil having density 981 kg per meter square. The shear stress at a point in oil is 0.2452 Newton per meter square, and the velocity gradient at the point is 0.2 per second. So mass density is 981 kg per meter square. Shear stress is tau is equal to 2452 Newton per meter square. Velocity gradient is 0.2 per second. So using the equation tau is equal to mu du by dy, mu is equal to 1.226 Newton second per meter square. And the kinematic viscosity is given by mu by rho, and it is 12.5 centimeter square per second, 12.5 Stoke. Another simple problem. Determine the specific gravity of a fluid having viscosity of 0.05 pies and kinematic viscosity 0.035 Stokes. So viscosity mu is 0.05 divided by 10 Newton second per meter square. Kinematic viscosity is 0.035 centimeter square per second. So using the relationship nu is equal to mu by rho, you get rho is equal to 1428.5 kg per meter cube. Specific gravity of the liquid is, being density of liquid divided by density of water, it is 1.43. Another simple problem. Determine the viscosity of a liquid having kinematic viscosity of 6 Stokes and specific gravity 1.9. Kinematic viscosity is 6 Stokes, 6 into 10 power minus 4 meter square per second. Specific gravity of liquid is 1.9, and mu is viscosity of the liquid. The specific gravity of the liquid is 1.9. Therefore, density of liquid is 1900 kg per meter cube. Now using the relationship, kinematic viscosity is dynamic viscosity divided by mass density. Nu is mu by rho. You get mu as 1.14 Newton second per meter square, that is 11.4 pies. Then another property is compressibility, which depends on the bulk modulus of the liquid. So compressibility is the reciprocal of the bulk modulus of elasticity, which you are familiar with. It is the ratio of compressive stress to volumetric strain. And compressibility is given by 1 by K, where K is increase in pressure divided by volumetric strain. Volumetric strain, you know, it is change in volume by original volume. Okay, and we'll see some of the problems here determine the bulk modulus of elasticity of a liquid. If the pressure of the liquid is increased from 70 Newton per centimeter square to 130 Newton per centimeter square, the volume of the liquid decreases by 0.15%. So we will see the answer now. Initial pressure is 70 Newton per centimeter square. Final pressure is 130 Newton per centimeter square. Therefore, increase in pressure is 60 Newton per centimeter square, whereas decrease in volume is 0.15%. So using the expression for bulk modulus and compressibility, you get bulk modulus as 4 into 10 power 4 Newton per centimeter square. So another simple problem. What is the bulk modulus of elasticity of a liquid which is compressed in a cylinder from a volume of 0.0125 meter cube at 80 Newton per centimeter square pressure to a volume of 0.0124 meter cube at 150 Newton per centimeter square pressure. So initial volume is 0.0125 meter cube. Decrease in volume is 0.001 meter cube. Volumetric strain is 0.001 divided by 0.0125, and initial pressure is 80 Newton per centimeter square. Final pressure is 150 Newton per centimeter square. Therefore, increase in pressure is 70 Newton per centimeter square. Therefore, bulk modulus is given by dP divided by minus volumetric strain. Therefore, it is 70 into 125, 8.75 into 10 power 3 Newton per centimeter square.